start with the CC. So for this also inversion formula holds. Okay, and finally, I'd like to end it here and this portion only. Finally, I want to go from L1 to L2. So in Euclidean Fourier analysis, what happens if you first we define Fourier transform on L1 via this integral, but if you take f in L2, this is not quite defined as an integral. But what to do is, suppose you can take the help of CC infinity or L1 in the section L2. All these are dense spaces inside L2, right? So for f in CC infinity, you can prove something called an isometry between the two spaces using the L2 norms. This is Rn. Again, there can be some constant here. So you prove this. So you can prove this for CC infinity functions which are in L1 as well as L2, and use the density of CC infinity in L2 to define the Fourier transform on L2. Okay, it's very simple. So it's like if you have given a function f in L2, you have a sequence fn in CC infinity. Is it becoming too small? I can't go to that. I just wanted to stick here with this portion. Anyway. So this is called the L2 version. I'll just tell you how to define the transform L2. So if you have f in L2, there exists a sequence fn in CC infinity such that fn goes to f in L2. So, and once you use this, that this fn, the L2 norms of both of these are equal, so basically an isometry you use. Then using that, you see that so these fn's are Cauchy in L2. From that you will get the fn hats are Cauchy in L2, and so they convert somewhere. That somewhere you define it to be the Fourier transform of this L2. Okay. So from using this, it will follow that fn hat, these sequences are Cauchy in L2, and so they will convert somewhere. There exists some g in L2 such that this fn hat converts to g in L2, and this g this is the Fourier transform of f. This is how you define the Fourier transform of f in L2. Anyway, this is the Euclidean thing. So after you define it like this, you can basically extend this to the whole. And that is the conjunction. So my aim is to do all of this on hyperbola. That is my aim. So
so the inversion formula is if f hat is in L1, then this inversion is
inversion formula, yes. For inversion formula, I forgot to write for almost every days. Yeah. So for inversion formula to hold, you need both f and f hat to be in it. Otherwise, this wouldn't make sense, right? I mean, for this to make sense.
F hat need not belong to L1.
No, for just defining f hat, you don't need f hat to belong to L1. Okay, it may not. But for this integral to make sense, you need f hat to belong to L1. Okay? So that's why. So this is what I plan to do. So hopefully I'll be able to cover up to Riemann algebra and some part of biphasic today, and inversion maybe tomorrow and last week. So yeah, we need machinery is there, so that we will develop. Okay, so this is what is the plan. Okay, I now maybe recall some of the things in. So you've seen Muna's lectures. So I will not go into the details of whether it's the H or D. Okay, I will just assume G. I will stick to this notation. Okay, so G for G, I have these decompositions A. So I will recall this whenever needed, but for now just let me recall some of them. So for G, I need KAN decomposition, and for this I will also put my notation. This I use sometimes. So for small g, I write this as Kg, exponential of Hg and Ng. This is the Higasawa decomposition. So this is Higasawa decomposition. And I will sometimes use the A decomposition, all of these are there. And there are different integral formulas. I'll recall them whenever I need them, not right now. Okay, and yes, and KX plus RKA. This is the polar decomposition. And there is another decomposition I need here. So here, what happens in polar decomposition? If you take plus, then if you take only the positive side, this A part is unique, but your K parts may not be unique. So there is another decomposition which makes those unique as well. If I need them, I'll then manage. So yes, and I need some facts. Like for example, another notation I need. N is the centralizer of A in A. Okay, so this here is actually just transferring plus minus identity. So basically all the elements which commutes with other elements. Just that. So I need this and I need some facts. So for example, one is maybe I'll write there because maybe I will call it for some of these. Some of you. It normalizes N. So which basically means that A inverse is contained inside N for all. Okay, and N centralizes A. So which means N equal to AN for all A and N. Here you understand A from capital A and N normalizes. Oh, is it small? Sorry. Okay, right. N. So, which again means this. N. N. Okay, so these are again some of the facts that we need. As of now, these are all we need. And yes, so now let's try to define this. Okay. So for this, and I'll be looking at functions on G by T, like which is same as D, which is same as H in particular cases, which Muna has already talked about. Okay. So here, first what I need in order to define this Fourier transform is the notion of this right side. So for that, Muna has also defined this. So E lambda K G is equal to E to the power minus I lambda plus 1 H part of G inverse K. Right? This was the definition of E lambda K G. And it also has some other things with respect to Z and B, all those things was done yesterday. So I'll stick to this notation. I'll not go to both the Z and B notations. So this is what is used to define the Helgason Fourier transform here. So that is defined as F tilde lambda K. So he had defined F tilde lambda K to be this. k. So g by k basically means functions on g which are invariant on the right under k. I will also need functions on g which are invariant on both sides under k. I'll call them by k invariant functions and come later. Okay. So this is called the Helgason transform. Okay. Now the question is, why did we define on f in cc instead of f in L1 here? I want to define this, right? If I want to define the Fourier transform, it's natural to consider f in L1. But so here remember why we could have defined it for f in L1, because this was bounded. This is equal to minus ix cross I. But here, so let's look at what happens to this. Okay. So here I have I lambda plus 1 where lambda is complex. Okay. And this part is of course h part of this g inverse k which is inside, comes from this Iwasawa decomposition, this part which comes from that at, Muna has denoted this as k, a, t, n, s. So it's basically this t part which is real. Okay. So this thing is real valued and here we have a complex part. Okay, lambda is complex value. So if you take the modulus of this, notice that minus lambda plus 1 h of g inverse k. If you take the modulus of this, what happens? The real part of lambda, that modulus becomes 1, but the imaginary part is left. So I have e to the power imaginary part of lambda minus 1 h g inverse k, which is a real number, right? So for any complex number, this may not be bounded, right? So only when say imaginary part of lambda is equal to 1, then we know that this becomes 1. Okay. Otherwise, if it's not equal to 1, then so only when imaginary part of lambda is equal to 1, I have lambda. This thing is equal to 1. Otherwise, if imaginary part of lambda is not equal to 1, this may not be bounded, and so you cannot do this, right? So that is why you are not able to define Fourier transform in this way for L1 functions, because okay, for yes. No, G was SL2R or SU1R. So the decomposition is Muna G already. Okay, so yes, G is SL2R or SU1. Okay, and correspondingly K, A, and N we are defined for SL2R. We are defined K, A, N. Correspondingly K tilde, A tilde, L tilde for SU1. Right. So those things. Okay, so K is compact. Here A and N are like R. Okay, so in this case we have that. PT is the Harmonic. PT is the Harmonic. Right. And we'll also have individual Harmonics on this, and depending on these decompositions, we will have different Harmonics. We will recall them whenever something is needed. So yes, here PT is the Harmonic. Okay, so that's why we are not being able to define on L1. So we need to do that. So for that, what we do is, instead of looking at this E lambda kg as such, which is not bounded except one line, okay? So we look at this with an integral around it, an integral over km. Okay, we just so that we call so for lambda in C, we define lambda g is equal to integral over k minus I lambda plus 1 h of g inverse k d. Okay, so inside is E lambda kg, we are just integrating over k. Okay, so that we can expect, I mean, maybe something better for this one. And then we can, I mean, somehow we can use this to define Fourier transform on L1. Okay. Ah, yes, thank you, thank you. Thank you. Yeah, it might be that. Okay, so these are called spherical functions. Spherical functions. I was supposed to recall some more things which I forgot to, so I recall them now. Some more things about, not recall, maybe I'll do also. So some more things about these which I need here. So, okay. So first, some properties I need about E lambda k's. So one is E lambda k is a right invariant function. Now the size is fine. Bigger? Oh, I think it's bigger. It's not. Okay. So this is sort of obvious from what Muna did, because this turns out to be functions on hyperbolic on D as well as on H. But anyway, you can also see it from, I mean, there's a easy way to see it in any case. So if you want to prove it, so there's a G inverse K factor here, okay? So, and G inverse K, you need the H part of it, right? So that means you need to break up in this K in decomposition and you need the H part, okay? So suppose you write G inverse K H as K1 AN. So that means this A is the H part of it, I mean not A, log A. So, and you need to prove that it is invariant under K on the right. That is, you need to prove that E lambda K G say K2 is equal to E lambda K of G. You need to prove this. So I can now put K2 instead of G and see that this turns out, this becomes K2 inverse, G inverse K, and G inverse K I have already written down as K1 AN. So notice that this part is in K, AN, so they have the same A part. The same A part means same H part. Okay. So this tells you that H part of G inverse K is same as H part of K2 inverse K, and that gives you this, because that is what's needed in defining E lambda, right? Okay, so this is the first property. Let me call it something very fun. Write bigger. Remind me about it. Okay. And another thing I need is if you take a function f from K part of inverse K, this Luna had written down but not proved. I will also not prove, but it is available. Luna had sent 2 notes to all of you, right? One was Professor Eskirai's notes, and otherwise his notes. It's there in both of them. Okay, so please refer to them for the proof. I just need, so one is Fk e to the power minus 2h part of Gk. It's better now. So here if you put f to be the constant function 1, you get, so what you get, this is 1 here normalized, here by dk I mean the normalized Cartesian on k, which is a compact group. So compact group, so you can normalize so that the total measure is 1. So here you get 1, and you just get on this side k e to the power minus 2h gk dk. This should get to be 1. Okay, so this is another fact that I need. Both of these formulas I need. Thirdly, I need G is also equal to E lambda K mg, where small m is coming this capital A, which I have defined. Okay. So essentially, what it will mean is that instead of considering the parameters from lambda, in case of lambda means from complex plane and k is from the group K, you can consider from K by U. So you can restrict to K by U for all. Okay. So this also, I mean, if you just want to get rid of it, so G inverse K you write as K1, A1, N1. Inverse K M, you write this K1, A1, N1, N, right? And here you use the fact that M normalizes N. So M and M inverse is inside N. So if you take some M, N, it will be of the form of N to N. Okay, for some N1 and N2. So you can write here that this is equal to K1, A1, M, N2. So here you will use the fact that M normalizes N. Okay, and then you can again use the fact that M centralizes A, right? So some people say, right? Yeah, M centralizes A. So that means these two will commute. So you get A1, M, A1, and 2. Okay. So, which essentially means now M is a subgroup of A, right? Because it is the centralizer of A in K. Okay. So M is inside K. Okay. So these two together is like K. This is A. This is M. So this is the A part of G inverse K M as well, which is same as the A part of this. And A part is like A part, between A part and H part, it's all the same, it's just there's a log range. Okay. So A part of something is just exponential of the H part. Okay, so this is also right. A, G, A, G. It's just so that is how you get H part of G inverse K is equal to H part of G inverse K M, and so these two are same. So basically, mostly, I mean, it will be like this. So playing around with these decompositions, different kinds of properties in between them. So mostly the calculations are like this. Okay, just playing around with them and getting the results. Okay. So this is another fact that I need. And finally, yeah. So this is another thing which is obvious, that for if you keep K and G fixed, then this function lambda going to e to the p lambda K G, this function, so see, as a function of lambda it is n, right? So these are all fixed. Lambda is a complex number, so this is, it's just e to the power minus I lambda plus 1 some times. Okay, so then it is an entire function. So this is okay, so these will be some facts that we need. Now, we had defined the spherical functions. We should come back to that because we are, remember, we are yet to define the Fourier transform for L1 functions. Okay. So yes. That is the hyperbolic space. That is the, I mean, that is the analysis of that we are doing. I mean, there are.
So G mod case hyperbolic.
Yes, yes,
Oh.
yes, yes. So that analysis is what we are doing. Okay. So whole thing I will be doing on functions on G by T. But for that, I will take the help of functions which are bi-independent also. So, and then use that to come back to here. That we will do later. But yeah, that is that. Okay, so we were here. If these properties are here, I will erase from here. Okay, I'll leave this right now so that I can keep this. So. So now first we wanted to, for this phi lambdas, I want to show that these phi lambdas are actually what we call bi-k-variant, which means if you put k on either sides, you can forget about it. Okay, these are invariant under k on both sides, both left. Okay, so this is something I want to do now. This is true for all k1, k2, k, and for all g. Yes, function of the upper half plane is like SL2 or by its k1.
Yeah, but then
It's invariant under the k action from the left, right? So, this is what are
invariant under the K action from the right, and it is also invariant under the K action from the left. That is an extra. So you can call it sort of radial functions on the upper.
I think he's asking that what will they look like? What will they look like?
Okay, yeah. So in this picture, the sphere is actually circular. So it will be same on
Yes.
depend on your hyperbolic distance from the origin. Yes.
Yes, the AT part only. That is located
Yeah, the upper half picture is from distance from one.
So yes, so if you consider this decomposition, say polar decomposition, you can forget about both the sides and it only depends on A plus. Yeah, it's the analog of radial functions in Rn. Rn, like if you take radial functions, means if mod x is equal to mod y, fx is equal to fy, those kind of functions. Yes. So, so I proved that these are k by invariant. These are called k. These type of functions are called k by invariant. I'll come to the definition and more properties later. So first, what is obvious? I asked you that. Which part is obvious? It should be invariant under both k axes from both the things. So which part is obvious? Right k invariant is obvious because of this, right? Because it has essentially lambda k inside its definition, and that is invariant under the right k. Okay, so obviously it is lambda is right k invariant. That is obvious from the right k invariance of E lambda. What is not that obvious is the left k invariance. So maybe I think K1G K2, which is right k invariant, so it is lambda of K1G. You can forget about K2. And if you write this, so what happens? You can write it like e to the power minus I lambda plus 1 h of now K1G inverse of K. So that is G inverse K1 inverse K and integrate over K, right? This is the definition of phi lambda of K1G. Okay? Now what do we do? Yes, so just look at this K1 inverse K. Okay? So this integral is over dk, right? It's over the k variable, and K1 inverse K is also inside K. So you just, this is just left translation of the K variable by K1 inverse. right? And we know Harmonic, you know, all seen through the lectures as well. So left invariance of Harmonic we use here in K, and we get that this is nothing but P lambda of. So you can just replace K here. This is Phi lambda of K. So that's how Phi lambda is by K invariant. And next, what we want to do is, so remember our aim was to define Fourier transform. So for that, and why did we want to do it? Because E lambda K was not bounded in a nice place; it was only bounded on the line. So next, we will prove is that Phi lambda is actually bounded on a strip inside the complex. So there we will be able to define Fourier transform on that strip. So using this boundaries. So that is the next result. For the next result, I should define the strip. So to define the strip, I have to do some conditions. So for 1 less than 3 less than infinity, I define what is called gamma p 2 by p minus 1. Okay. So for here, so that will mean gamma 1 is equal to 1. The standard ones. Just note down gamma infinity is minus 1 and gamma 2 is 0. Okay, just and some more properties we'll need, which are all to see. I'm not going to do that. Just very simple formula. So all of gamma p will be modulus will be less than equal to 1. It will be between minus 1 and plus 1. Okay, so for all three, and gamma p is equal to minus of gamma p prime, where p and p prime are the conjugates. Okay, so these are some properties I need, and not only that, all of these are modulus is less than equal to 1. The whole interval minus 1 1 is given by gamma. So the minus 1 1, if you take anything from there, it will be of the form gamma p for some. These are all very easy to see. Very simple. Okay, so I'm not going to do anything. So these we will need. Why? Because the strip I was talking about, it's just a strip where imaginary part of mod z is less than equal to 1. Okay, in the complex plane, so it's basically this strip. Okay, this is plus 1, this is minus 1. Okay, it's basically this strip. But what we are going to do is, I want to write it as the union over the lines alpha plus I gamma p for all alpha in R. So this strip, you can break it up into all lines, and since all the gamma p's together constitute this minus 1 1, so wherever it is, depending on that, you have a gamma p corresponding to it. So wherever it is inside this strip, it will be of the form of some alpha plus I gamma. Okay, some real number alpha plus I gamma. Okay, so this is the expression of the strip that I need. Yes. This is called Henderson-Johnson strip. So they have learned all my whatever I know from Judah and Shantala and everything. They are the experts, so better to ask them. Now, we were supposed to prove that phi lambda is bounded. I keep this. Okay, these things I will just. write it as alpha plus I gamma p for some alpha and some b, right? So for lambda in S1, there exists some p and some alpha in R such that lambda equal to alpha plus I gamma. Now, for p greater than 1, we look at phi lambda g. That is basically phi of alpha plus I gamma p mod. Now, phi lambda expression I deleted, but anyway, I hope you remember that is just the integrals of the E lambda case over here. Okay? So if I take this inside, take the modulus inside the integral, I can write this as e to the power minus I alpha plus I gamma p. Remember it was minus I lambda plus 1. So alpha plus I gamma p plus 1. So this was the expression and h of g inverse k modulus of this over dk, right? So here again, I alpha things inside the modulus and this is real, it becomes modulus 1. We are left with this part. So that I can write as e to the power gamma p minus 1 h of inverse k. Okay. And just if you calculate here, this maybe I haven't written down here, but write down gamma p minus 1 is it just comes to be minus 2 by p inside this expression that will follow. So it is equal to integral over k e to the minus 2 by p prime h of inverse k dt. Okay. And p prime is a conjugate. And now what do? You want this to be finite somehow, right? What do we do? It is just e to the power minus 2 by p prime. We can use I have erased. We had something like this integral over this minus 2 of this thing was finite. Remember the properties I wrote down? 1, 2, 3, 4, one of them. The integral over so integral over e to the power minus 2 h inverse k dk, that is finite. That is 1. That we do. So how do we do? Holders basically. Okay. This by p prime. Okay, and it's a compact. Okay. So if there is by p prime, so you put you apply holders to the power p prime, and the other part you can take as 1 because it's a compact. Okay. So just apply holders inequality. So h inverse k dk, and the other part will be 1 essentially, and this to the power 1 by p prime. But this thing inside is 1 that we have seen, so the whole thing is 1. Okay, so for any p greater than 1, this quantity is bounded by 1. And also for p equal to 1, what happens for p equal to 1? For p equal to 1, gamma 1 is just 1. So if you put it here, it is just 0. So this integral becomes 1. So for p equal to 1 also, p lambda this thing is okay. So you have this theorem that for any lambda inside this strip, you have phi lambda of g. This modulus is that given one, so it's bounded in the strip, this straight line. And it is also known that outside this strip, it is up. That is known. That is called Helgason-Johnson theorem. So we will restrict to this strip because outside unbounded thing is also known. So now we will want to define Fourier transform for L functions on the strip. the definition is already there. I mean, I don't need to define it again. I just need to prove that it's finite and it exists, right? That is what I'm doing. So if f is in L1 by K, then there exists a set K naught inside K with full measure. Full measure basically means measure of K is equal to measure of K naught. Okay? So with full measure, such that for any K in K naught, integral over G f G mod of that e to the minus I lambda plus 1 h inverse K modulus of that, this quantity is finite. And this is true for all lambda in S for the whole string. Okay? So we had defined the Helgason Fourier transform using the boundedness of E lambda K. We only got it on one line, and now using the boundedness of we will define it for the whole string. Okay? This is the thing. Okay. So let's start. So again, let lambda be S1. So again, I can write lambda as some alpha plus I gamma p. Now, so how do I prove this? So what I do is, this as such, I cannot prove it to be finite. Right? So I again apply a K integral. Okay, so I just basically use the result by function is in L1. If its L1 norm is finite, then it is pointwise finite almost. Okay, so that is what we will use. Okay, so that's why I do this with full measure thing. Okay. So almost everywhere it is finite. Is it okay? So I just this implies f(x) is finite for almost every x. This is what. Okay. So that's why what we do is here we put a K integral outside. Okay. So e to the minus I lambda plus 1 h of inverse K modulus of that dt and dk. Okay. So this is my that thing. Okay. It's somewhere. I have defined first. Defined first. Yes. No. Because whether it's finite or some integral, you don't know. Density won't help you find it. Because even in Rn also that doesn't help, right? Because in Rn, this L1 only exists. For L2 also it is dense, but it doesn't. So, okay, so we are looking at this. Now, this we can write as G. And here, this one is again lambda we are writing as alpha plus I gamma p. But this time, let me write it as minus I gamma p here plus 1 because alpha anyway modulus is 1. So if we write it like this, note that the thing inside what I have here, what is this quantity? This is nothing but phi lambda. I don't have the expression of phi lambda on the board, but this is nothing but phi at I gamma, right? So this was the expression of phi lambda where you had lambda here. Okay, so it is just phi at I gamma. So I have integral of G mod f G of I comma p at g dg. Okay, so this was the expression. Now this I know this was bounded by 1 on the strip, and we had a modulus, but this is a non-negative quantity and it comes from this point. This expression is what we had. So this is bounded by 1. So I have this is less than equal to integral of f g dt, and this is nothing but L1 of f of I. Okay. This is how this integral over k helps, and this boundedness of p lambda helps. And we have this quantity is finite, but wait, I mean we are not done, because why are we not done? Because this lambda here depends on p. So what we have got here, so from here we can say that this inside integral is finite almost everywhere with respect to k, but that set k on which it is finite, which is a full measure, that depends on p. I need to get rid of p. Okay, I need a set which does not depend on p. Okay, since lambda was depending on p, I have this p dependence which I want to use now. So, but I'll give some name to that set. So from here I get that is this. From here I get that there exists a set kt subset of k with full measure for each p such that for each kp I have that this quantity inside this mod ft, and this one I can write as for gamma p minus 1, that is what it calculates to be h of x inverse k tk. This is finite. It's visible up to this, right? Okay. So for each p, I have a set of full measure kp for which this holds when my lambda is already I have gamma p minus 1. Okay. So I need to have something independent of p. So I define k0 to be k1 intersection k infinity. Okay. So for each p I have such a kp. I just take the one for 1 and the one for infinity. I take their intersection. If both of them are full measure, then this k0 is also full measure. And so this integral actually, so if I start with this integral set, I just break it up into two portions. So in one portion, I take all those g in g. I have that name. G plus is g such that h of inverse k is greater than or equal to 0, and g minus is everywhere this is less than 0. Same h of g in this case less than 0. Okay, just divide it into two parts. So I can write it in g plus. So yeah, so I just write this integral on both of these cases. One is where h of g inverse k is non-negative, one is where it's positive. When it's non-negative, note that this thing is non-negative, okay? And gamma p minus 1, this quantity is also non-negative because remember the gamma p was between minus 1 and plus 1. So gamma p minus 1 is always negative. Gamma p minus 1 is always less than equal to 0. Okay? And here, if it is non-negative, the two of them together make it to be less than equal to 0. Okay? So on G plus, this quantity is dynamically divided down. Gamma p minus 1, h of x inverse k, tk, and same here. Now, this quantity is always less than equal to 0, right? Because of gamma. Gamma is always less than equal to 0. And here, less than equal to 0. If this is less than equal to 0, e to the power this is less than equal to 1. And 1 is what we get when this is just if we put p equal to 1. So this is just less than equal to gamma 1 minus 2 because gamma 1 is 1. So I can just write it like this. So because we have taken k1, that's why. So that this is finite. And here it's the opposite. This is again less than equal to 0 always, but this is here less than 0. So both together it becomes non-negative. So for that I have to approximate with gamma infinity. Okay, so gamma infinity is what? Gamma infinity is minus 1. So minus, if you put gamma infinity is minus 1, so it is always less. So if you put gamma infinity is minus 1 and this is less than equal to gamma p always, and you are actually multiplying with the negative quantity, so the inequality reverses. Okay, so once the inequality reverses, you get this. Okay, now so this is dominated by this and this quantity is dominated by infinity. So and you have taken k1 intersection to infinity. Here this is finite for those, and this both of these are finite. So this was just done to get rid of the p dependence. Okay, so you get a set k naught independent of p for which this whole thing is fine. Okay. So essentially what you have done is you have been able to define Fourier transform for L1 functions on G by K on the entire strip. Right? Lambda is coming from the strip S1, that unit strip between imaginary lambda is between modulus is less than. Okay. So we are done with. So here we have like this was a difficulty which we could get over and we have defined. Okay. This seems like we find a bit difficult today. Anyway, I'm going very slow, is it? Is it too slow? So next our aim is to prove Riemann Leibniz. For that, we will need the notion of radon transform. Okay? So let me So, and also some things I just didn't mention that, yeah, because of the lambda here, when you define it like this, you have holomorphicity in the strip. So whenever you can define it, and then the usual holomorphicity through it, you have holomorphicity of the strip. So you'll have things like, I mean, if it cannot be compactly supported, if it is 0 on a big region, then it cannot, it will be 0. Okay. So, let me go to radon transform. Okay, for radon transform, what I have to do is, I'll start it. So I'll notion of radon transform. So that definitely motivate from R2. Okay. So suppose F is in F1 of R2 and psi is a point in R2. Now F is psi. I think right. So the definition by definition, this is R2 Fx minus I x dot psi dx. Right. Now I can write this as so on. So remember, I have a decomposition. I can write psi as SW, where my S is somewhere in infinity and W is an element of the substance. It is just the polar decomposition of form. Now, here, what I can do is I can write any element of X like on TW plus UE1. I need E1 also. E1 is also a unit vector which is orthogonal to W. Okay. So I can write, so basically omega and E1 are two unit vectors orthogonal in R2, then spare the whole space, right? So any X you can write as TW plus UE1 and integral of R2 you write as DTT. Okay, so you just write this as e to the power minus I minus I S. So psi is SW. I am writing this as S TW plus UE1 W. Okay. So SW is psi and your X is TW plus UE. Okay. And this, so this is just DU. Okay. The R2 integral I am just dividing it to R integrals. Du and the R integrals. U and the other integrals. Yes, sure. So basically you have say xi here, okay, and so it will be of some distance s, and towards the direction w. So w will be the point here, xi will be somewhere here, say, okay. So this is just the polar decomposition, remember, and for W here you will have something perpendicular to it. Okay. Yes, this one. Okay, so basically I am decomposing R2 in terms of these two directions. Okay, W and D. So, and yes, yes. Oh, sorry, I don't want. Thank you. Yes. Sorry, it's 0. Okay, so that's how this is explained. So this SW is xi and this is so W and W, the W is a unit vector. So that gives you norm is 1 and E1 W is 0. So that's how you get this. Okay. So this quantity D, so this quantity. So if you are writing like this, but it is essentially over R f of TW plus UE1. It is essentially e to the power minus IST, right? Like you calculate this, you get back this. Right? W W is 1 and E1 W is 0. Okay. So this quantity du inside because it becomes independent of that. dt is outside. So this quantity inside is called the radon transform. Okay. So this is the so radon transform at f in the direction w. Okay. So it is basically you integrate along, so on this what happens, that TW is varying over W, right? So, so the W is fixed and U thing is varying. So it is on, so it should be this line, right? No, from a distance G. So, Yes, so it will be this line, right? This line, no? Perpendicular to W, this line, and from not S here, so at a distance T that. Yes, at a distance T. So this line, okay? So this is what Una was referring as the hyperplane. In Rn you have a hyperplane, in R2 you have a line. Okay, so it's at a distance T along the direction of that. I mean, okay. So this on this. The indication on that is called the radon transfer. Okay, and it's noted as RFWT. Okay. So, and note that if you call this RFWT, this is nothing but the Fourier transform of it. Okay. So you have RFWT is your variable. So you write it like this. Have that. S. Right? So just look at this expression. So your fx is this. Okay. So this is the just note that this is the one variable Fourier transform on R, and let's start with the two variable Fourier transform. Okay, on because f was on R. So this is how you define radon transform on R2, and similarly you can define radon transform on this homogeneous spaces also. So, and also it is easy to see that this RFWT is actually in L1, because how do you see that? So if you say look at this RFWT, which is defined, so this thing is defined here. Okay, so this can be this is less than equal to, you have to take two integrals, one is outside and one is coming from inside the expression of RF. So and you have TW plus UE1, and you have TU, T both, right? And both. If you vary both T and U, you get the whole out. Right? So this just turns out to be nothing but that is finite because F is in L1, that's what that's happening. Okay. So the fact that it is in L1 of R is clear, and then its Fourier transform is. That is how these two are connected. Now we want to do the same thing on hyperplane spaces or G by K. So I just simplify. I start with f of L1 of G by K. I know what is f in the lambda K. This is fg e to the power minus lambda plus 1 h inverse k dg here. Okay. Now I just do a change of variable. I take g going to kg. Okay. So that will put the k here, and we'll get rid of the k inside this. So I have this. Okay. Now I have to use one of the decompositions and the hard measure corresponding. I have to recall that. Yes. I'll use a result. I'll prove a result using this, and then use that to prove the result. Objective is demanded. And radon transform in general is also important, because after this also, when we go to the K bi-invariant situation, that time we will need Abel transform, which is the bi-invariant version of radon transform. Okay. So, I mean, it is anyway needed. For now I need it for demand. becomes minus t, because if my g I'm writing as NSATK1, then g inverse will be K1 inverse, AT inverse, which is A minus T, and NS inverse, again N minus S. Okay. So from here I get this minus T. This is the H1. Okay. So here and with the hard measure you actually have a minus 2T, TK1, TS, T. So okay, in this decompositions Muna had written down, but anyway to recall I just write down. So you have N, A, K, F, you have this decomposition. The hard measure looks like this. Here in this decomposition it's twice log A, this factor comes in. K, T, A, T, N. So this is how it looks like. Okay, so this factor is okay because I have used this decomposition. Okay. So once we have this, we can write we can get rid of this K1 because F is on G by K, which essentially means that we can get rid of this K1. This you can find that this will become into the, so I can write this as okay, so I can write it as KNSAT. I rather write this as KAT, A minus T, NS. I just put AT, A minus T, their inverses in between because I need them. And here and e to the power I lambda t, e to the power minus t, ts dt. Now, why do I need this? Because again, Muna had done this. A minus T ns AT. This also follows from the fact that A normalizes N. Okay. So this is nothing but N e to the power minus 2Ts. In case these are all very basic computations, you have the expressions of all of them. In T you know how it looks like in the matrix. NS you know how it looks like. These are just matrix multiplications. If you are like not sure about this, just multiply 2 by 2 matrices and see. Okay, it's very easy. So once we have this, then this becomes F, K, A, T and N e to the power minus 2Ts. That's what we get from there, right? And we have here e to the power lambda t, e to the power minus t, yes, t. Now you make some change of variable e to the power minus t s to s, so that you get another e to the power. So this e to the power 2t then comes to the measure. You just make this change of variable. E to the power minus 2ts goes to s. So this comes in the measure, and finally you get F, K, A, T, N, S, because we've made that change of variable. You can take S inside and this R. I'm sorry, I kept on writing G. I should have rather written 3 integrals. So one on K, another on R, another on R. Okay. So these should be replaced with 3 integrals. Okay. So depending on the calculation. So here I have R and one more e to the power t to put here and another R here. So you see that this becomes here the I lambda t. Yes, oh sorry, there will be, this K integral was over K1, which I had got rid of, so there will be 2 integrals. that this thing inside is your error. Okay? So this is what is Reynolds transform. I define this and I tomorrow I will accordingly plan tomorrow. This is my Brayton transform of F. And again, you see, this is the Euclidean fluid transform. Okay, again, similar to what we did for the Euclidean case. Okay. So here, the Fourier transform R2 is connected with the one-dimensional Fourier transform of Reynolds transform here, and similarly here, the Laplacian Fourier transform is connected with the one-dimensional Fourier transform of the. So yes, I